everyone. Thank you for attending my talk. I'm Yuan, a fourth-year PhD student from Northeastern University. I'm going to talk about our work, online caching networks with adversarial guarantees. This is a joint work with Tarek, Giovanni, and Stratis. In a cache network, when a request is generated, it is routed to a designated server, which permanently stores some contents. Each node is equipped with finite storage space, which could store the item and serve them. As a result, during traveling from user to designated server, upon hitting a cache, which stores the requested content, the request will terminate early. A response carrying the requested content is generated and backpropagated over the reverse path. In this work, we would like to explore how to place content in caches to minimize the total traffic costs. Actually, content allocation in networks of caches has been explored in the offline setting, which presumes demand is known. The problem is NP-hard, but admits a 1-1/E polytime approximation algorithm. To study dynamic caching, some work consider requests generated following Poisson process and network being in steady state. Furthermore, some work explores caching algorithms that comes with adversarial requests other than stochastic ones. Most of this work focuses either on a single cache or on simple bipartite network topology. Apart from this work, we are trying to meet two challenges. First, we would like to explore a network of caches represented by an arbitrary topology and requests for the content arrive in an adversarial fashion. Second, we would like to take updates costs into consideration rather than consider total traffic costs only. Corresponding to these challenges, we make the following contributions. First, we revisit the cache network with arbitrary topologies from an adversarial point of view. Second, we propose a distributed online algorithm that attains O square of T regret with respect to an offline solution that is within a 1-1/E approximation from the optimal. Third, we also extend our algorithm to account for update costs. We show that an O square of T regret is still attainable in this setting when using coupled caching decisions. Finally, our model can be extended to consider joint optimization of both caching and routing decisions. In the remainder of this talk, I will overview our work from three parts. First, I will start with how we formulate our model. Think of we have a network represented as a directed graph G. Assume that we will assign a weight W on each edge. This weight could be routing costs or delays when the contents traverse the edges. As a cache network, each node has a cache with finite capacity CV. And there is an item catalog C. It is the universe of items which can be stored in the caches or requested by the user. We use storage slot S to represent each storage space in the caches. In this figure, each small square is a storage slot, and it can only store one item. Since each node V has a capacity CV, each node has in total CV storage slots. We can then describe the content allocation by the set A, where each element small a equal to Si indicates that item I is stored in the slot S. The feasible allocation requires each storage slot can only store one item, formulated by this constraint. There are some nodes that permanently store items called designated servers. So no matter what content allocation is, requests can always be satisfied, either by the caches or these designated servers. A request R is a pair of item I and path P. These paths are predefined starting from the user to a designated server. In our setting, we assume that time is slotted and requests arrive over a total T rounds. At each round T, a set of requests RT arrive in the network. We make no probabilistic assumption on request arrives RT and wish to minimize regrets in the adversarial setting, that is, with respect to the worst case sequence RT. Given the above inputs, we could calculate the cost of serving a request by the first equation. In this example, once the request hitting a cache, a response is back-propagated in the reverse direction. Thus, the routing cost is width of these two red edges, which is 8. Caching gain is the routing costs when all caches are empty minus costs with cache allocation A. In this example, the routing costs without cache is 18. After minus cost 8, the caching gain is 10 here. In the online setting we studied, requests are not known in advance. In particular, at the beginning of the round T, an online algorithm selects the current allocation AT. Then requests RT subsequently arrive, and the cache gain FA is revealed. This is raised in total T rounds. As in standard online learning literature, we use regret to measure how good algorithm is. Regret is the differences between the total cache gain by the online algorithm and that of the best fixed decision in hindsight. Let's first figure out what is the best allocation in hindsight, which is the offline setting of this problem. In the offline version of the problem, the requests sequence RT are assumed to be known in advance. The goal is then to determine a feasible allocation A that maximizes the total caching gain during entire T rounds. This problem is NP hard. However, the problem is monotone and some modular maximization on their partition matrix. There exists polynomial approximate algorithms that produce a solution within 1 - 1 over E from the optimal. To the best of our knowledge, this is the best guarantee. Then the regret of our online problem is with respect to the gain obtained by an 1 - 1 over E offline approximate algorithm, which is 1 - 1 over E regret. Our goal is to find an online algorithm with sublinear 1 - 1 over E regret. This implies, on the average, our online algorithm generates an allocation strategy as good as a static policy that has full hindsight of the sequences. When changing an allocation from AT to AT plus 1, it requires the movement of item, which incurs update costs. We denote by W prime SI the cost of fetching item I as storage slot S. Then the total update cost is given by this equation. When such update costs exist, we need to account for them when adapting caching allocation. We thus incorporate them in the 1 - 1 over E regret as an extended one. This extension corresponds to adding the expected update costs incurred by the policy A to its 1 - 1 over E regret. Same as before, we design sublinear regrets. Then we propose a distributed online algorithm to obtain such sublinear regret. Basically, Each slot maintains a probability table. They make their decisions according to it. When a request is generated, it's propagated over the path until a hit occurs. A response is then back propagated over the path, carrying the item and incurs routing costs. At the same time, an additional control message is generated and propagated upstream over the entire path. Moving upstream, it collects information from slots it traverses. After reaching the designated server at the end of the path, the control message is back propagated over the reverse path. Every time it traverses a node, each storage slot fetches information stored in the control message and computes a reward. Having this reward, each slot updates its probability table respectively. These are the new probability tables. Finally, each slot stores a new item according to its new probability distributions. There are two ways to select these contents. One is independently select cache item only according to its probability distribution. This one is simple, but incurs more update costs. Another one is coupling this selection with the presently selected content. While yielding the same expected caching gain, coupling can bias the selection towards items already existing in the caches. This reduces update costs, especially when probability distribution changes slowly. Theoretically, neglecting update costs, our distributed online algorithm with independent caching decisions achieves sublinear 1-1/E regret. While incorporating update costs, we evaluate the algorithm through extended one, as I pretended before. Unfortunately, the update cost of independent caching decision grows as omega t in expectation, thus loses the sublinear extended regret. Nevertheless, the extended regret can be reduced to O square of t by modifying our caching decision from independent one to the complex coupled one. With coupled caching decision, both standard regrets and expected update costs grows as O square of t. As a result, the extended regret is also sublinear with respect to horizon t. Finally, we experimentally prove the superiority of our algorithm. We use 4 synthetic graphs and 3 backbone network topologies. We also consider 3 different types of synthetic request generation process and 1 trace-driven use a real-life trace from a CDN providers. The algorithm we compiled with are first, the path replication with LRU, LFU, FIFO, and RR eviction policies. Second one is PGA. This is attempts 1-1/E approximation guarantee in expectation when requests are stationary, but comes with no guarantee against adversarial requests. Third one is GRD. We prove that its 1-1/E regret is omega t in the worst case. Last one is our algorithm. In the first simulation, we explore the performance of different algorithms with respect to time average caching gain across multiple topologies. We observe that our algorithm TBGRD, GRD, and PGA have the similar performance across the first 5 topologies, with GRD being slightly higher performing than the other 2. Nevertheless, on the last 2 topologies that given designed adversarial requests, both GRD and other myopic strategies have poor performance, attaining a 0 caching gain. This also verifies the suboptimal of the GID. Then we want to compile caching gain at update costs incurred by independent caching decision, showing on the left, and the coupled caching decision showing on the right. Recall that theorem states that both decisions lead to the same caching gain in expectation. This also verified experimentally by results in the first row. We observe that they both lead to almost identical time average caching gain. We also observe that the accumulated update costs showing in the second row is vastly different across the two. The cumulative update cost of the independent one is more than 15 times compared to the coupled one. In summary, we consider a general caching networks in adversarial setting and propose a distributed online algorithm that achieves sublinear 1-1 over E regret for the adversarial caching gain maximization problem, even when accounting for update costs. An interesting future research direction is to provide regret guarantees for the class of path replication algorithm. Another important future research direction is to consider dynamic regret. That's all for today's talk. Thank you.